Welcome to this professional course in Industrial 4.0. This module on ecosystem for smart farming will cover the introduction to agriculture and aquaculture 4.0. Let me introduce myself. I'm Associate Professor Dr. Margaret Chan Kit Yok from the Faculty of Plantation and Agrotechnology, University Technology Mara, Malaysia. The aim of this course is to provide an introduction to agriculture and aquaculture 4.0, its major components, processes and technologies, and how new products and services will impact business and society. 3 objectives, and they are: number 1, provides an overview of precision farming concepts and the tools of precision farming that include GPS, GIS, and VRT. Secondly, it introduces the use of each of these tools within the processes of a precision farming system. And thirdly, discuss economic and environmental benefits. At the end of this course, the learner should be able to understand the various stages of industrial revolutions, understand the future of agriculture and aquaculture and the skill set needed, recognize the drivers, enablers, and compelling forces for agriculture and aquaculture 4.0's advancement, identify the role and importance of data and cloud computing in agriculture and aquaculture 4.0, and finally, describe how organizations and knowledge benefit workers who can better prepare for agriculture and aquaculture 4.0. At the end of this course, the learner should be able to understand the various stages of industrial revolutions, understand the future of agriculture and aquaculture and the skill set needed, recognize the drivers, enablers, and compelling forces for agriculture and aquaculture 4.0's advancement, identify the role and importance of data and cloud computing in agriculture and aquaculture 4.0, and finally, describe how organizations and knowledge benefit workers who can better prepare for agriculture and aquaculture 4.0. Are you ready to move on to lesson 3? It will be on auto guidance system. This lesson will cover 2 units: components and technology of auto guidance systems and drone technology. The keywords are auto guidance system, agriculture vehicles, drone technology, precision farming, and intelligent fish farming. The first subtopic is on components and technology of auto guidance systems. In the current scenarios, the agriculture labor force engaged in farm or fishery production is gradually entering the aging stage. The labor shortage makes it difficult to guarantee the normal supply of global food and industrial products. Rising energy costs and more reasonably priced auto guidance systems have made a clearer cost justification for investment in this new technology. So what do we mean by auto guidance system? Auto guidance system refers to the guidance of agriculture vehicles using satellite-based positioning equipment, example GPS receivers. The most obvious benefits include reduced skips and overlaps, lower operator fatigue, ability to work in poor visibility conditions, minimal setup and service time, and ease of use. The 3 levels of automation for steering an agriculture vehicle are navigation aids, auto guidance, and field robots. Relatively inexpensive navigation aids, known as parallel tracking devices or more commonly light bars, are being used by operators. They are able to visualize their position with respect to previous passes and to recognize the need to make steering adjustments if a measured geographic position deviates from the desired track. More advanced auto-guidance options include similar capabilities with the additional options of automatically steering the vehicle. It uses either an integrated electro-hydraulic control system or a mechanical steering device installed inside the cab. When implementing an auto-guidance option, the operator takes control during turns and other maneuvers and oversees equipment performance when the auto-guidance mode is engaged. Finally, with autonomous vehicles, the operator's presence on board is not required, that is, in robotic mode. The entire operation is controlled remotely via wireless communications. The field robots can be very beneficial, for example, when applying chemicals that are hazardous to human health. However, the greatest liability of autonomous vehicles is that improper response in unpredictable field situations has been the major drawback of robotic agriculture. Otherwise, auto-guidance would have been recognized as the most promising option for today's farming operations. Like in any other type of system, radio signal processed by receivers can be affected by several factors. Example, atmospheric interference, configuration of satellites in the sky, and time estimation uncertainties. The applicability of uncorrected position estimates is rather limited. To adjust estimated geographic coordinates in real time, various differential correction services are used. In addition to the differential correction, most receivers apply signal filtering techniques. This is to assure the best possible predictability of antenna location. Based on the quality of differential correction and internal signal processing, positioning receivers used for auto-guidance have been advertised according to the level of anticipated accuracy in submeter, decimeter, and centimeter. Widely used in agriculture and other industries, single-frequency receivers with submeter level accuracy frequently rely on several alternative differential correction services provided by public and private entities. Popular in the past, the Coast Guard Differential Correction AM radio signal, also known as the beacon, is broadcast through a network of towers located near navigable waters. More recently, Wide Area Augmentation Station (WAAS) has been deployed by the Federal Aviation Administration of the U.S. to broadcast a satellite-based differential correction service. A similar service is available through free of charge John Deere Starfire 1 or SF1 and subscription-based OmniStar Virtual Base Station VBS options. To achieve decimal level accuracy, dual frequency receivers can be used. They are provided with subscription-based John Deere Starfire 2 SF2 or correction services with a local-based DGPS stations. In the centimeter accuracy level, a local-based station is also required to implement a real-time kinematic differential correction service which provides the ultimate centimeter level of accuracy. In certain locations around the U.S., local networks of permanent RTK-based stations have been established by private entities to provide fee-based coverage of areas with relatively high demand for superior positioning accuracy. Control of vehicle dynamics becomes more challenging when in situation of farming slope ground. Thus, roll, meaning tilt from side to side, or pitch, tilt from front to back, and yaw, turn around vertical axis, alter locations of the positioning antennae with respect to other parts of the vehicle. For example, when driving along a slope, the horizontal position of the antennae located on the top of a cab shifts to one side of the tractor with respect to the projected center of the tractor. This causes an engaged steering control system to guide the vehicle so that the point directly below the antennae and not the center of the vehicle would follow the desired path. To compensate for these attitude cost challenges, most auto guidance systems include a combination of gyroscopes and accelerometers or several antennaes placed in different locations on the cab. A gyroscope sensor is a device that can measure and maintain the orientation and angular velocity of an object. These are more advanced than accelerometers because they can measure the tilt and lateral orientations of the object. An accelerometer is a tool that measures proper acceleration in the linear direction along one or several axes. Proper acceleration is the acceleration or the rate of change of velocity of a body in its own instantaneous race frame. This is different from coordinate acceleration, which is acceleration in a fixed coordinate system. Less advanced terrain compensation modules can deal only with roll and pitch angles, while more sophisticated sensing systems, frequently called 6-axis, can measure the total dynamic attitude of the vehicle in space. Vehicle stability and proper alignment of the implement attached to the vehicle are also important when implementing auto guidance. If a skip followed by an overlap takes place with every alternating path in the opposite direction, when making straight and level trips from one end of the field to the other, a properly adjusted pull implement will not follow the slope terrain. In that case, the implement will tend to stay close to the center of a turn or shift downward. Several manufacturers have addressed implement tracking solutions that allow accurate sensing of the implement's position with respect to the vehicle and mechanical adjustment of this position. They use a set of large diameter disc counters to overcome the occurring side shift. Additional developments are focused on compensating for known shifts of the implement by adjusting the vehicle trajectory to assure proper tracking of the implement instead of the vehicle. Optical and mechanical clock-based guidance systems can also be useful when it comes to the position of the implement with respect to previously established roles. When adapting auto guidance to a particular farm operation, it is necessary to understand that positioning error is just one factor causing less than perfect field performance. In addition, the ability to maintain desirable geometric relationships between passes is affected by vehicle dynamics, ability of the field implement to track behind the vehicle, and actual conditions of the field surface. Therefore, poor quality of the steering control system, slope terrain, or misalignments in the implement will cause the overall field performance to suffer. The intelligent fish farm is an all-weather, full process and full space automated production mode. In the case of workers, they are not entering the fish farm. The new generation of information technology such as IoT, big data, AI, 5G, cloud computing and robots are used for remote measurement and control of fish farm or robot-independent control of fishery facilities, equipment and machinery. This would complete all production and management operations of the fish farm. Finally, intelligent fish farms rely on digital and intelligent technology to solve the problems of aquaculture, labor shortage, water pollution, high risk and low efficiency. It is the industrial transformation of fishery production mode and the development direction of fishery in future. Intelligent fish farm can be divided into 4 categories according to different cultural environments. They are the pond type intelligent fish farm, land-based factory type, catch culture, and intelligent marine range. Pond type intelligent fish farm collects water quality information using sensors in real time and unmanned aerial vehicle patrol to obtain the water surface activities of the fish. The growth status and feeding process of fish are observed by bionic fish, and the water quality is regulated by fertilizing and spraying chemicals on unmanned boat. Bait is transported by unmanned vehicle. DO is accurately controlled by intelligent aeration system, and the intelligent bait feeder realizes accurate and automatic feeding. Intelligent harvesting is carried out by automatic throw machine and fish distributor. Only when all systems work together in an orderly manner can the reliable operations of the pond type intelligent fish farm be guaranteed. Land-based factory type intelligent fish farm is also known as automated recirculating aquaculture or RAS. This fish farm mainly integrates microfilters, biological filters, intelligent feeding machines, aquaculture tailwater purification and utilization devices, as well as advanced model and intelligent equipment technologies to construct a fish circulation 3-dimensional aquaculture model. Based on the deep study of relationship between the basic requirements of aquaculture biology and the operation parameters of RAS system, scientific decision-making on the optimal culture density, appropriate water environment demand, and efficient aquaculture management strategy of fish under the recycling aquaculture mode are carried out by extensively collecting production data and integrating big data analysis technology. By integrating high-quality seed production and selection technologies, the fish farm establishes a supporting technology of good breeding methods suitable for circulating aquaculture and realizes the whole process of parent fish mating, egg hatching, flight cultivation, adult fish breeding, sales, and packaging. In cage-type intelligent fish farm, seawater quality and ocean current information are obtained using sensors, fish movement and feeding information using machine vision and sonar. The feed barge can deliver bait accurately according to water quality, fish biomass, and feeding behavior. The underwater net is cleaned autonomously by the net washing robot. The automatic fish catching work uses automatic net lifting systems and the fish pump. light supplement, and emergency oxygen system can be used as an emergency control of water quality. Cage-type intelligent fish farm can be of two types, the floating type and the fixed type. It will form a three-dimensional aquaculture mode according to the water layer where different aquaculture objects live. The feed, energy, and other production materials will be transported from the land-based warehouse to the breeding place by unmanned vessels. Cage-type intelligent fish farm can relieve the pressure of offshore resources and effectively solve the problem of land-based aquaculture as it occupied a lot of space. Intelligent marine rangers usually use high-definition surface cameras and underwater robots to collect the video information of the range in real time. The video information is transmitted to the data server in the shore-based information control center using the transmission network for the purpose of biological identification, behavioral analysis, and biomass estimation. With reference to the previous illustration, the range obtains the ocean current data and the distribution of plants and animals near artificial reefs by installing Doppler sensors, underwater cameras, and sonars. The range then uses water quality monitoring buoys, weather monitoring stations, management boats, radar, and other underwater mobile monitoring equipment to provide the automated all-round monitoring of the marine range. According to George 2014, using satellite remote sensing technology, SRS, marine rangers can evaluate the fish stock variability in different space and time scales. Based on the interaction between microwave and sea surface microscale structure, synthetic aperture radar remote sensing technology can remotely sense ocean current, cyclone, and other fishery-related marine environmental information. The feeding method in range can choose to use unmanned aerial vehicle to spread feed in the air or choose to use unmanned boats to close the water surface for autonomous feeding. The material supply for marine range is usually transported by unmanned boat in the way of land-sea relay. Now we move on to the next topic on drone technology. Drone technology is giving agriculture a high-tech makeover. An autonomous flying tool that has a pre-planned flight or control by remote is called a drone. Unmanned aerial vehicles, UAVs, may one day consist of autonomous swarms of drones collecting data and performing tasks. The biggest obstacle to that becoming a reality is sensors capable of collecting high-quality data and number crunching software that can make that high-tech dream a reality. In agriculture, drones are mainly used for imaging for the identification of weeds, planting area, fertilizer, and weedicide application, and real-time weather forecasting. Autopilot drones with a camera mostly are used controlled through GPS. The use of vision algorithm enable drones flight autonomously. Different sensors are used for takeoff, flying, and landing of the drone. Sensors like accelerometer, gyroscopes, digital compass, and barometer helps the drone while the flight to detect motion, that is the position and speed in the environment. These GPS sensors detect specific field information from geostationary satellites. Minimum 3 satellites are required to define the longitude and the latitude, and one satellite assesses the altitude of the UAV. Basically, the satellite data is merged with other data for a higher level of precision and accuracy. This vision helps in agriculture field through disease and weight identification and for crop health monitoring. Here are 6 ways that drone can be used throughout the crop cycle. Number 1, soil and field analysis. Producing precise 3D maps for early soil analysis. Drone can play a role in planning seed planting and gathering data for managing irrigation and nitrogen levels. Number 2, in planting, startups have created drone planting systems that decrease planting cost by 85%. This system shoot pods with seeds and nutrients into the soil, providing all the nutrients necessary for growing crops. Number 3, relating to crop spraying, drones can scan the ground, spraying in real time for even coverage. The result is that aerial spraying is 5 times faster with drones than traditional machinery. Number 4, crop monitoring. Inefficient crop monitoring is a huge obstacle. With drones, time series animations can show the development of a crop and reveal production inefficiencies, enabling better management. Number 5, irrigation. Sensored drones can identify which parts of a field are dry and in need of improvement. And lastly, health assessment. By scanning a crop using both visible and near-infrared light, drone-carried devices can help track changes in plants and indicate their health and alert farmers to diseases. Drones can do a lot of work above and below the water for the aquaculture industry. The fish farms, whether it's on land or in sea, and especially offshore aquaculture sites, can be monitored. Many works, including the checking of holes and damages in cages, can be carried out by drones. Most importantly, drones can collect novel information which are difficult to be obtained by humans. This information can be used to generate algorithms for further developing technologies to improve the efficiency of aquaculture production. In combination with AI and cloud computing, it will cut costs and improve operations for the aquaculture industry. This is the end of Lesson 3. I will leave you to spend some time for self-reflection with 10 multiple-choice questions in the quiz. Congratulations to have completed this module on Introduction to Agriculture and Aquaculture 4.0 Ecosystem for Smart Farming. I wish you all the best and thank you.